Okay, now I want to do another example of partial pressures. Before I do that, I want to make sure you know a few things before I go in to partial pressure. First of all, STP stands for standard temperature and pressure. At standard temperature and pressure, temperature is 273 Kelvin and pressure is 1 atmosphere. Okay, so that's just, if you see STP, if they say this is right at STP or standard temperature and pressure, they're just saying that it's at 273 Kelvin in 1 atmosphere. That's just the standard. And if you put that into PV equals nRT and you solve for it, at standard temperature and pressure, the volume is 22.4 liters. Okay. And that's just another thing. So standard temperature and pressure also has a volume. So it's almost like STPV. So standard temperature and pressure, 273 K, 1 atmosphere, and 22.4 liters. Also, if you have a density problem, remember density is moles. No, sorry, I'm thinking of molarity. Density is grams per milliliter typically. And so we can use PV equals nRT. So we have PV equals nRT, right? And we want grams per liter. So if we move everything around, we can get moles per liter, milliliter here, N over V, moles over volume, equals P over RT. Anyway, you can, and then you have to multiply the molecular weight because you don't want this in moles, you want it in grams. So, long story short, hold on. Okay, so basically, once you derive and you put everything in there and you convert moles to grams, so you can get the density. You get this formula here. So density equals to pressure multiplied by the molecular weight of the compound divided by your R constant and temperature. Anyway, I just want to show you, so if you do have a density problem, here's how you could do it. And you could just do it with PV equals nRT. But there you go. So if you do it, you literally just plug in all the numbers there. So an example here, they have calculate the density of a nitrogen gas at 125 Celsius. So that's your temperature. You convert to Kelvin. So you put your temperature right there in Kelvin. You choose your R value. Here's your pressure, millimeters of mercury. You convert that to atmospheres. Oops, wrong way. Millimeters of atmosphere. And then we're looking at nitrogen gas, which is N2. So you put 14 times 2, so 28 in there. So you put all of your numbers in there, put them in the correct unit, and then literally get density. So this is kind of a plug and chug formula. Just in case you see it, I just wanted to show it to you. So partial pressures, this is basically, you have a container filled with many different gases, and each gas has its own pressure. Okay, so if we look at this example here, we have helium, neon, and argon. So we have a container filled of helium, neon, and argon. They each have their own pressure. And the reason the pressures are different is because they're different gases, okay? And they're different sizes. So they're going to have different velocities. Anyway, so the pressure, the total pressure is whenever you add up all the individual pressures, okay? So that's sort of what partial pressures is basically if you add up all of your individual pressures, you'll get your total pressure. Other formulas that are important are mole fraction. So mole, meaning the amount, equals to the moles over total. So let's think about what that means. Okay, so if I have, this says my mole fraction, this is just a symbol for it, equals to the amount of mole of the substance, so let's say we have moles of hydrogen, over the moles of the total. Okay? And that gives you the fraction. I mean, that's just like any fraction we've done before, you know. Let's say we have a total of 10 gas particles, or we'll say 10 gas moles, Okay, let's say 3 of them are hydrogen, 7 of them are neon. I don't know. Okay, so what's the mole fraction of hydrogen? Well, the total is 10. Okay, and there's 3 hydrogens, so it'd be 3 over 10. That is the mole fraction, or if you want to divide it out, it'd be 0.3. Okay, so that's all the mole fraction says. It's the part over the whole. And the other one would be the partial pressure. So this is basically says here, the other formula that's helpful with partial pressures is PA equals to your mole fraction times the pressure total. Okay, and this makes sense if you think about it. Okay, so basically this says that let's say, so this is the pressure exerted by, let's say, hydrogen. So we have a pressure by hydrogen, and let's say that hydrogen, let's say that the total pressure is 10 again, and let's say that hydrogen takes up 80% of the pressure. Or let's do the one we just did. We did 30, right? 0.3. Okay, so this tells us, because that's the moles, because it takes up 30% of the volume, 0.3 is 30%, and you multiply that by the total, okay, so that'll tell you that the pressure of that is, 3, okay? So basically this tells you how much pressure is exerted by that individual particle, okay? So if out of 10, hydrogen takes up 3 of that total pressure, okay, if that makes sense. Okay, so again, if we had a container, okay, and the total pressure in here, total pressure equals to 10, okay, we said hydrogen takes up 3 atmospheres, because that's what we just said, okay, and we had neon before, okay, so then how much would neon take up of that? 7. Okay, so it just tells you individually what it contributes, if you want. Okay, so hydrogen contributes to 3 atmospheres of the total, or 30%. So basically, it's a way to calculate the individual pressure. Okay, so we're about to do this kind of long, hairy problem, but we can do it. Okay, so let's really think about what we're doing here. This problem here is easy. I mean, I'll just tell you. It says the partial pressure of oxygen in air is 0.21 atmospheres. So oxygen is 0.21 atmospheres, argon is 0.01 atmospheres, and nitrogen is 0.78. So this says individually, oxygen takes up 0.21 atmospheres, argon takes up 0.01, and nitrogen is 0.78. What is the total pressure? So the total pressure, remember, is all the individual pressures added together. So you just had to add up 0.21 plus 0.78 plus 0.01, and that should equal about 1 atmosphere. Okay, so your total pressure is all the individual pressures added together. Okay, so let's look at this one. This is the one that's a little bit crazy. So let's just write down all our numbers that we have, and then think about what we're calculating. Okay, so a 1 liter mixture of helium, neon, and argon has a total pressure of 662 millimeters of mercury at 298 K. Okay, so we have our volume is total of our volume total, because it says a mixture of all of these added together is 1 liter. So we're going to say our volume total, if we want, is 1 liter. Let's see, it gave us a pressure. See, I wrote this down. Here it is. 662 millimeters of mercury, and that's the total pressure. And then the temperature was 298 K. So let me show you where I got those numbers. 1 liter It says a mixture of helium, neon, and argon has a total pressure of 662 at 298. So I have volume total, pressure total, temperature total. Now, if the partial pressure, so the individual pressures, that's what partial pressure means, of helium is 341 and the partial pressure of neon is 112. Okay, so let me put those down here. So pressure of helium is 341 millimeters of mercury, and pressure of neon was 112. And let's see what we're solving for. What is the mass of argon? Okay, mass is in grams, so we want to know mass argon. Question mark. This is going to be in grams. Okay, so let's look up here. We have a container. Let me draw my container over here. And in this container we have helium, neon, and argon. Okay, we know helium takes up 341 millimeters of the total pressure, and neon takes up 112. Does it make sense that more than likely, since we're trying to solve for grams of argon, we're going to have to know that pressure of argon? We know the total pressure is 662. So before we start this problem, actually, let's convert all our units. So liters is fine, kelvins is fine, but let's put this in atmospheres. Atmosphere, so 1 atmosphere, let me give you the, equals 760 millimeters of mercury. So if you look here, P total, let's see, 662 millimeters of mercury. Millimeters of mercury at the bottom to cancel it out. 760. 1 atmosphere. So all we're doing is dividing by 760. So 662 divided by 760 is 0.871 atmospheres. And if we do the same here for these, so we divide all of these by 760. So divide by 760. Divide by 760. So they're all in atmospheres. Let me change my color. Put it in green. So now these are going to be, so helium is 449.9 atmospheres. And neon will be 0.147. Okay, so let's see what we have here. We're trying to find grams of this. Okay, so one thing is, it gives us all the pressures of these except for argon. So more than likely we're going to have to figure that out. Okay, and we need to get to grams. So let's see what this gets us. So we have 449 for helium, 0.147 for neon, and we know the total is 0.871. So let's use that. So we know that the total pressure is 0.871, and we know that we know that helium is 0.449, plus we know that neon is 0.147 pressure, and we don't know the pressure of argon. Remember, in our container here, we have helium, neon, and argon. We know helium takes up 0.449 atmospheres of pressure. Neon takes up 0.147. And we're trying to figure out argon. And we know the total is 0.871. So we know when we add them all together, it needs to equal to this. So let's figure out argon. So if we add these numbers here first, 0.449 plus 0.147, we get 0.871 equals to 0.596 plus argon. Okay, now bring this over to solve for argon, and argon argon pressure then equals to 0.275 atmospheres. Okay, so that would be 0.871 minus 0.596. Okay, so let's make sure. So when we add up 0.449 plus 0.147 plus 0.275, it should equal about 0.871. Okay, because that's what all of them individually added together should equal to. And when we do that, you do get about 0.871. So this is correct. Okay, so we know the pressure of argon is 0.275. Okay, so we know that. Now let's go back to that one formula I gave you where it says that, let me change, since I'm doing kind of a different problem, pressure of the individual, so the pressure of argon equals to the mole fraction of argon times pressure total. Okay, now why would I want to use this? Okay, first of all, I have my total pressure, remember it's given up here, and we put this in atmospheres. I just solved for pressure of argon, so here and here. So I have these numbers. What does mole fraction give me? Well, let's write this down. Mole fraction, argon, equals to, the mole fraction is, remember, moles of argon over moles total. So it's the part over the total. So part over the whole. So why would I want this? Well, because I'm going to get moles, right? What do I want to end up with? Grams. Can I convert a mole to a gram? Yeah, really easily, just using molecular weight. So if I can get moles of argon, I can easily convert that to molecular weight. So I have to start here first, though. I need to get this mole fraction. Okay, so I know my pressure of argon is 0.275 atmospheres. And I don't know my mole fraction, so I'm just going to put the mole fraction. And my P total is 0.871. So if I divide these two numbers together, and that's in atmospheres, I'll get my mole fraction. So when I do that, when I divide those numbers, my mole fraction is, let's see, 3.16. Yeah, 3.16. Okay, so I have a mole fraction, so I'm getting closer. Okay, so I have a mole fraction. Remember, this is what mole fraction equals to right here. Let me see if I can put a box around it. I'm not very good at this. Okay, so I solved for this. Okay, so now I have this number, but I don't want mole fraction, I want actual moles. So I have this number, so I need to get moles total so I can get moles of argon. Well, that's where all of these other numbers come in. Remember, we wrote all these down, they are for something. So we can put in PV equals nRT and solve for N. You see that this is volume total, pressure total, this is temperature total. So when I do this, I'm going to get moles total. Okay? So let's do PV equals nRT. And let me change my color again. Let's do black. Okay. So I have PV equals nRT, PV equals nRT, pressure is 0.871, so pressure total. My volume is 1 liter. How do I know that? Because it says up here, volume is 1 liter. So my temperature is 298 when I get to it. And I don't know, I'm solving for R is 0.0821 and temperature is 298. Now how did I know that was my R value? I like to look at my units. So I have a liter, I have a Kelvin, and I converted this to atmospheres. So I have a liter, Kelvin, atmospheres. So I have this pulled up on Wikipedia here. Gas constants. Okay, here are all my gas constants. So you have to look up the one that has a liter mole atmosphere. Okay, so this is a joule Kelvin mole. That doesn't work. Keep going down. Anyway, here's one. You see liter atmosphere Kelvin mole. Those are the units I use. So that's the R value I use. So it's whatever units you use. For your other numbers, that's the R value. Okay, so 0.821. So when I solve for this and I get N, I get that N equals to, this is N total, 0.036, right? Yeah, 0.036. Okay, so now let's look what I have here. I have moles total, which I can put in right here. I have my mole fraction, I can put in there. Then I can get moles of argon. Okay, so write all this stuff down, or let me erase part of this. Oops, okay, or I delete everything. Okay, so I have, let me write down what I have here. I have not that. Okay, I have my mole fraction. That's what I'm about to use. I saw, and mole fraction is moles of argon over moles total. I just solved for moles total and said it was 0.036. I know my mole fraction of argon is, where did I put that? 3.16. Okay. Now let's remember, we're trying to solve for grams of argon. Okay, so if I can get moles, I can get grams. So let's put this in. I have 3.16 is my mole fraction equals to moles of argon, which I'm trying to find underneath there, and then my moles total are 0.036. So I'm going to multiply those out. So I get moles argon equals to 0.113. Okay? So I'm almost done. I know you're like, oh my goodness, there's another step. Well, yes, because I need to convert moles to grams. Okay? But I'm almost there. So I have moles. I want to cancel out moles and get to grams just using the molecular weight. So I look here, what is the molecular weight of argon? Right here, it is about 40. So I have 40 grams in 1 mole. So 0.113 times 40. This equals to 4.55 grams of argon. Now I know, that was a huge long problem. I tried to warn you beforehand. But think of these as fun. I know you're like, seriously, how could that be fun? but they're puzzles. You have all these formulas and you just have to figure out which one to use. Okay, so when you're doing all of these, let me show you the 3 formulas that you need to use when you're doing mole fractions or partial pressures, really. Okay, these are the 3 formulas that will come into play. You will be using not that. Let's see. PV equals NRT. Okay, and that's, anytime you have a gas problem, it talks about a gas, this is the formula you'll use anyways. So PV equals NRT. Mole fraction is moles of A over moles total. And remember, when you're this here, PV equals NRT, boop, this is for the total of everything. So your moles total is right here. Your pressure total is right here, volume total, all of those are total. The other one is, let's see, what did we say? Oh, yeah. Pressure total is pressure A plus pressure B plus pressure C, etc. However many there are. So these are the 3 formulas we use. We had to kind of go back and forth between them to figure it out. So anytime you have a partial pressure, these are the formulas you need to go to right away. And then you just have to figure out what order do you use them in. Okay, so if you think of it as only 3 formulas and just plugging things in, and it looks hairier than what it was because I had to, first figure out this one. Then I had to figure out this one to get to this one, to get to the grams. So it looked a lot worse. But really, we're just doing 3 formulas, so it's like 3 steps. Okay, so this one says that if you add up all the individual pressures, you get a total pressure, which makes sense. Okay, so if my container has helium and argon, okay, if I add up the pressures of helium and argon, I'll get the total pressure. The mole fraction says the fraction is the individual moles divided by the total moles. Okay, so that's just your fraction. How many moles of helium are in the total amount of moles? So that's just your fraction there. And then PV equals NRT will help you solve for any of these you're missing. Okay, so usually what you're going to end up doing is using one of these 2 first, and then somehow at the end plug it into PV equals NRT is usually how they work. Anyways, I hope this gives you another example. These just come with practice, I'm going to be honest. Eventually, one day, you'll be like, wow, these are fun. But practice them, and maybe one day they will be fun to you.